Hi there. In this video, we're going to discuss work done, some different types of energy, and work through some examples that calculate the amount of work done on an object in a couple of different ways. So to set the stage, when we talk about, well, first there's types of energy. We have a kinetic energy in physics, and we also talk about potential energy. Now, kinetic energy is what we call the energy of motion. So if a car was to be moving down the highway, depending on its mass and its velocity, it would give you a measure of how much energy that object has, which is kind of a measure of how much work it could do, let's say if it were to run into you and you go flying off. So that's the type of energy that that object could have. We also have a potential energy, and potential energy is just a way of saying that energy is stored in an object. It could be stored in a number of different ways. We think of chemical potential energy. That's the energy stored in the bonds that make up the material itself. Dynamite would be a great example, has a number of very strong chemical bonds, and that chemical energy can be released. That potential can be released. The elastic energy, we store up most little cars and things that you would wind up and go, either have springs or elastics and bands in them, and that's energy that is stored up in those elastics. There's gravitational potential energy, which basically lets you know how much energy would be stored or work could be done on an object based on its position in the gravitational field. The higher an object is above the surface of the Earth, the more potential energy there's stored in that object. And electrical energy is another type of potential energy. They're stored in capacitors and anyway, there's a number of other types of energy. Those are the main ones we'll deal with. So we're going to work with what we call mechanical energy, and when we refer to mechanical energy, we're referring to the total amount of kinetic and all potential energies that we want to deal with for an object. So all of the kinetic energy plus potential energy would equal this mechanical energy. So we're ready to talk about what work means in physics versus what work means in your world. So a force, we could talk about a force doing work on an object when it makes the object move. So for there to be work done, you must have movement. You must have a displacement. So there's a force pushing, and if there's a resultant displacement, then there's been some work done. If there's no displacement, there has been no work done. If you push on the side of your house all day, then according to physics, you will not have done any work because the house hasn't moved. So you could look at this picture. We have a chair and a fancy couch. If you were going to push those two across the room, would it take more work to move the couch across the room or down the hall to another room? So if you just moved this over a certain distance, a small distance across the room, you'd have a certain amount of work done. If you moved it really, really far, there would be more displacement. Therefore, the work done would be more. So the work done is proportional, directly proportional to the displacement of the object. Okay, so what does that look like as a formula then? If you had to calculate work, we use the symbol W, and we simply work it out as force times the displacement. It's just F times displacement, which I'll use as delta D. So these forces the force has to be in the same direction as the displacement. If the force isn't in the same direction, that's why there's a little symbol on here of parallel. If the force and the displacement are not in the same direction, you will have to resolve that problem and mess around with the force until you get it in a parallel force, so that it's the same direction as displacement. And that comes up a bit more in vectors, which we aren't going to see right now. But it's just a caution or a caveat that you have to make sure that the force and the displacement are in the same direction. So displacement and force are both vectors, yet their product is a scalar. Scalar means that there's no direction to it. When you figure out work done, you're just figuring out joules, which is an amount of energy. You don't worry about what direction the energy is in, because it's not. Work done is a scalar quantity, no direction at all to it. All right, so let's look at a specific example. So let's say a physics student is rearranging her bedroom, she decides to move her desk across the room a total distance of 3 meters. So this will be the displacement of the object, 3 meters. So delta D is 3.0 meters. And she does this by at a constant velocity, so it's not accelerating. And she's doing this by exerting a horizontal force of 200 newtons. So the force applied is 200 newtons. 2.00 times 10 to the 2, letting us know we have 3 significant digits. And this was 3.00 meters. And we want to calculate the amount of work done. Well, we've learned that work done is the force times the displacement. Just to double check, my force is in this direction, or her force, I guess, is straight ahead, and the displacement is in that same direction. So force and distance, same direction, then we're clear and good to go. So we'll move that out of the way. My work done will be a force of 200 newtons, and we'll multiply that by a displacement of 3 meters. So that gives me a work done of 600, and we have whatever a newton times a meter is. And we saw in the previous slide that a newton meter was equivalent to J, or joules. So we have 600 joules of work done. All right, and no direction needed. If the force was west and the direction was, or the displacement was west, we don't consider the work done to be in the western direction. It is just a quantity of energy, and it's 600 joules. Okay, so we'll step away from the video. My students will have a chance to do some practice problems.